Neoventi.
So I'm also going to apologize for the fact that I put these slides together mostly today. So typos will probably abound, and if not, I apologize for making it not look bad. So what is a computer for? Because technology cannot be extracted from its context. Technology is created for a reason. And computers exist mostly for how we use them. To actually get stuff done, to do work, to do research, to talk to people. The point of a computer is what we do with it, not to spend forever working on making the computer itself better. So with that in mind, I'm going to get into why I'm rewriting my file system. So once upon a time, I bought a computer that ran Windows 10, and it had 2 gigabytes of RAM. So needless to say, a few minutes on the internet later, I found out what Unix was and was getting rid of the entire operating system. So, but where before it barely managed to turn on in 5 to 10 minutes if it was lucky, and spent 90% of its time on swapping to eMMC, it ended up able to get complicated games at 60 frames a second without any difficulty. So computers, when you remove a lot of the layers in the garbage, are capable of quite a lot. And a couple years after that, I was complaining about Linux to somebody for the umpteenth time, and they mentioned Plan 9 and that I would probably appreciate it more. So having a spare ThinkPad lying around, as one casually does, and having discovered that the front had fallen off, I grabbed a USB, put 9front on it, and started playing with it. And initially I was using CWFS just because that was the default option in the installer, and I had no idea what any of the options meant. So I just didn't think about it until it crashed and the ThinkPad lost power and the file system got corrupted, and suddenly I spent a little bit of effort thinking about what my file system was. The file system was completely recoverable, to be completely clear. The data loss was entirely because I didn't bother recovering it properly because I had a perfect excuse not to. But I also wanted to toss Plan 9 on a server at the same time, so I decided, hey, why not just play around with Venti, because I've heard really good things about using it in network setups. So I started messing around with it. And at first I just set it up in addition to CWFS and started tossing like media and such on it. And I'm just gonna also quickly note that the man page, really Acme? The man page has a very accurate complaint that setting up the server is way, way, way too complicated. Having never done it before, I think it took about 2.5 hours just to figure out how to format the freaking thing, which is a significant downside compared to the other file systems where you can just hit enter in the installer and have it work. So I did eventually get it working and playing with it, and for a while that went okay. I was using it for archival, for music, tossed some games on it, some PDFs just to play around with it, kept some archival root scores of like my home file system, and it mostly went well, so I decided to grab Fossil and actually try and use it as a file system. And that also mostly went well until I found a 4 gigabyte RAM module to toss in my ThinkPad, couldn't figure out what to do with my now 8 gigs of RAM, and went, hey, let me throw it at the cache. Because everyone, like in the Linux world especially, always talks about how unused memory is wasted memory. I've got 8 gigs of memory here, I might as well do something with it. And now seems like a good time to take a break from what happened there to talk about what Venti actually is, so that I can get into why things immediately went wrong. Venti is a network storage system which effectively has 2 primary operations. You give it a blob of data, it gives you an address back. You give it the address, it gives you the blob of data back. And it's content address, so these addresses have nothing to do with where on disk the data is stored. It's just a hash of the data. So if you write the same data to a dozen different machines, all completely independent, all with different sets of data, you're going to end up with the same address. You can read it back from any of them easily. So this can be used to set up like load balancing or replication pretty trivially, or a caching system. But in general, if you write the data to multiple Ventis, you get the same address. So if you read the blob back from all of them, it should always be the same. But storage devices are basically just giant blobs of data. Since Venti is giving a hash of data and it's just picking the address based on whatever it decides, which I'm not getting into just yet, it has to also keep track of where information is. So it has a map of the addresses it gives you, which are SHA-1 hashes of data. And it basically just keeps track of the value of where on disk it's physically storing it. So if you write the same data to 8 Ventis, each of them will give you the same address, and then it'll write internally, actually, I put that in a completely different spot from all the other ones, but shh, don't tell the user that. So when a write comes in from the client, it basically just finds the end of the data log, creates an entry, puts the data there, bumps the counter, puts the entry in the index, and then hands the address over to the client. And I ran this earlier just to make a demonstration, but if I run the exact same code right now, you can see the hash is literally the same because it's the same data, same place. And I'm sure if I were to take the time and effort to actually manually scan the disk, I could find what address it picked, but I don't care that much, and I don't think anyone else does either. But the basic concept is then if I had this empty data log and I gave it that right, the index just now has this one entry saying, hey, it's at address 0, and if we look at the beginning of the data log, the data's there. So when I then go and do a read for that data, it's able to know, hey, let me find that in the index, there's your data. So it just looks up the index, looks up the data log, it gives you the data back. So this system as described is functionally complete. You give it data, it stores it as a hash table on disk. It's just also pretty freaking slow because it's a hash table being stored on disk. It needs to do index lookups, it needs to then look up the actual data. And if you're doing a file system with this, that means a lot of index lookups, a lot of data lookups, a lot of back and forth. So it ends up being extremely slow. So of course it has a cache, and in fact Venti uses 3 of them for reasons I'm going to get into later. So when I decided to bump the cache from 100 megabytes to about 2 gigabytes, it immediately crashed because Venti was using signed 32-bit integers to store its memory sizes. And it decided, hey, let's try and allocate 1.9 gigabytes instead of the 2.1 you asked for. So I fixed that, found some other issues, fixed those, and the more I started actually using this system to run as a computer to work on actual projects. Let me put my music collection on here. Let me work on some code project, do some art, whatever. I kept running into these actual issues. And eventually I gave up trying to fix them and decided to rewrite the system from scratch. And I could go into a very, very, very long explanation as to why. But I have a much easier solution, and I apologize in advance for this. This is attempting to install Go 1.17 to the root file system. And now it's hanging, and if I attempt to open a new window, it just crashed the file system. And I'm sorry, but I'm going to have to reboot that computer now. This is a consistent problem. This is not the first time this happened either. About 6 or 7 months ago, I ran into the exact same issue, spent 6 hours debugging Fossil, found a fix, submitted it to a mailing list that got basically no responses, and then I found out a couple weeks ago that the patch was merged into 9 Legacy and nobody told me. So there are a lot of issues with this system, and the long story short is that trying to fix them is a loser's game because the system is not failing because it's not failing because of minor issues. It's failing because while the design of Venti and Fossil at a high level is pretty well done, the design of the implementation is absolutely atrocious. And it's severely over-engineered, so trying to basically patch it over with duct tape just results in finding even more problems to deal with. So let me kill draw term if I can figure out how to do that. And reopen it. And grab a new IP address. Okay. Okay, that went well. So with all of the context it's explained, it's probably actually helpful to go into the technical details of how Neoventi works, how it compares to Venti, and how it actually solves the design problems. So just as one quick, very simple example, this is the implementation of the hello of the protocol, where the server and the client start greeting each other. So in Neoventi, it basically, the Venti protocol starts by negotiating the version of the protocol itself. And after that version negotiation is done, we receive the hello packet, make sure it is actually the hello packet, that it contains the correct version of the protocol that we speak, which is 2.2 for whatever reason. I have no idea why, and this is not documented anywhere, nor is there any history explaining how this has changed over time. It just sets the version of the server effectively, just because I labeled it no, and I don't remember why I did that either, and then just sends that hello packet back. For comparison, here's the same code from the original Venti prototype. And the first thing to notice is it's significantly longer. The second thing is probably that it does multiple rounds of memory allocation and deallocation of data that it already has. It uses multiple layers of abstraction, so it has the foreign call wrapper over the packets over the actual memory. That packet interface is 1,000 lines of code, which is used to defragment this memory, which is coming in as single packets of data over the network and therefore is not fragmented. And in fact, while it's documented as existing for performance reasons, I tested disabling it and it was 10% faster. So there's a lot of places where Venti makes some questionable decisions and then puts a lot of code on top of it to make up for it. Whereas what I decided to do with Neoventi, and this is mostly relevant in that Neoventi is largely a response to this tower of abstractions. I wouldn't normally do things like, hey, let me grab a buffer from the client and reuse the buffer in place instead of generating a new one. But I was writing this after hours of frustration dealing with the original Venti, and I went, I'm going to do the exact opposite of what they did and use absolutely no abstraction here whatsoever, just manipulate the bytes directly. And so a lot of it ends up being, a lot of the design ends up being simpler just by not overthinking it. So as one very fun example also is the, Venti has that memory abstraction layer, and that's actually where that caching problem came in. Because malloc and free, believe it or not, don't take in signed 32-bit integers. Venti had a wrapper around it, vtmalloc, which did. And simply by not using that wrapper, the bugs went away. And there's a lot of these places where it's just doing a lot of things it does not need to do. And the term, I think it was Casey Moratori who used the term pessimization as the opposite of optimization, where rather than taking the time, basically there's a couple different strategies to optimizing code and trying to make things perform well. You can just write a bunch of code and then run it through a profiler and take the time and effort to actually make it better. Or you can avoid pessimizing it by just not overthinking it, not doing things in dumb ways. Just take the time to design things and a lot of problems disappear. And one particular example of how this actually works out in practice is that Neoventi has one cache. All it caches are raw disk blocks. So anytime it goes to read data from disk, whether that's the actual data you're asking for or the index entries it needs to get there, it reads 8 kilobyte chunks even if it only needed 2 of the bytes in it. And it will cache that entire block. Venti has an identical cache, but on top of it, it has an index cache and it has a lump cache. This is actually where some of the complexity for configuring it comes from and why it requires multiple separate parameters for how big you want the cache is. And each of those caches is implemented separately. So in the original Venti, it has 3 entire implementations of caches, each with its own free list management, with these doubly linked lists, and all of these locking structures, each of which is complete, like almost identical to the other 2, and yet completely redundant. And Neoventi only has that one cache. And so you might think that it might be a struggle trying to compete with this much older project and to beat it in performance. But in fact, even before the cache was implemented, it was only about 10% slower. And with it, oh, right. So what I just did is I have this archival file system, which is stored in the root in Venti on my computer. It's a copy of my root file system from a couple months ago when I first started working on Neoventi. And I now have 2 copies of this mounted in the namespace. One of them is a copy that's using Venti, the same Venti that's running the file system that's showing this presentation, i.e. the one that I crashed earlier in that demonstration. The other one is going through Neoventi. And if I take the time to walk through them, just to see how long it takes to go through the file system, it also occurs to me I totally forgot to bump the font size the second time through. I can totally type today. One of the things that I noticed when I was working on this and what prompted some of the Neoventi work to begin with is on my ThinkPad I have this nice handy hard drive indicator light. And when Venti is doing this right now as it's going through, 90% of the time it's doing this, the light is off, and the rest of the time it's just flickering on and off. That was the cold read. Without the cache, it took about 14 seconds. If I then do the same thing again, interestingly, that hard drive light is still flickering. Despite the fact that 100% of the data it's accessing fits in cache, it is still actually accessing the hard drive, and it takes 11 seconds to access it again, slightly faster than uncached. By comparison, for Neoventi, the uncached read currently has the hard drive light completely solidly on. It's not even flickering off. From previous experience, this is probably going to be something like 20 seconds, so it's a little bit worse than uncached compared to Venti. Whereas once it's cached, the hard drive light never turns on and it finishes in about 4 seconds. And more interestingly, looking at the profile of it when it does, the entirety of the time it spends on CPU on the server is spent waiting for the client to ask for data. The actual I/O to disk doesn't even register, nor does the locking, nor does the caching. It is spending the entirety of its time waiting for the client to ask for more information. I ran it through a profiler once when the cache there was a bug in the cache, which I'll get to shortly, because it's actually pretty technically interesting compared to the rest of it. But for the most part, this performance is not because it's doing something smart that Venti isn't. It's because it's just not taking the time and effort to allocate memory and copy things around that it doesn't need to be doing. It's not using 6 separate locks for one piece of information when it could just not do that. And a lot of this really does just come down to if you just write less code and spend more time thinking about what the code does, suddenly a lot of these issues are gone. I literally, the first time I ran this walk of that root file system, it worked immediately. That is more than I can say about when I actually set up Venti, the original one, the first time. A lot of the reason this exists is just fix up the issues with the design, avoid overcomplicating things, and I want to be able to stop thinking about my file system so that next time I want to go and upgrade Go, I don't notice that my file system crashes when it's installing. I just want to be able to use Go. That's really all this is I spent weeks and months going over Venti trying to fix all of its bugs, and I realized it would take less effort not to even bother. And I'm just going to, I think there was a little bit more in here, but yeah, for the most part, yeah, no, that's it. The only thing in here that's really actually technically interesting in its own right is probably the cache. Everything else is just do things in the easiest way possible. The cache, I maybe over-engineered a little bit and spent a good couple of days reading every single paper I could find on hash table and cache implementations. To the best of my knowledge, this is the most memory efficient cache for disk usage in the world right now. And the way it does that is by cheating. Very, very, very hard. Because most of the time when you're using a hash table for some cache, you end up, what I've seen for most of these hash tables is they're designed generically. You have some key, you have some value, you don't really care that much about what the data is, because you design these tables as libraries. Any application is supposed to be able to just grab the library and use it. But it turns out if you actually are paying attention to what the data you're working with is, you can truncate a lot of that information and make things ridiculously efficient and fast. So, for instance, one of the main things, the main way this works is there's a paper called the CLHT, the cache line hash table. And the only thing that this hash table does, which again, it's not over-designed, it's just do things in an obvious way and do it right, and you get good performance out of it. All it does is design each of the buckets of the hash table to fit in one line of cache memory, which means 64 bytes. The original paper was using 8-byte keys and 8-byte values, which with the locking and the cleverness they managed to work in there, meant that at best they could get about 6 entries per cache line, usually 4. I made some changes and I'm currently at 8, and I have some design changes to get it up to 12. But the basic idea here is the keys are 4 bytes and the values are 3, because all that this is caching is data from disk. And all it's caching is blocks, and each block is 8 kilobytes. So I don't even need 64 bits of address for what I'm caching, because I'm not storing 2 to the 64 bytes of data. There's no need to address that. So if you have, say, a 64 terabyte system with 8 kilobyte blocks, and you just want to be able to index into these, it turns out that you can actually get away with 16 bits of information for, well, actually, what I'm basically doing is, Venti splits the storage into arenas. So each of them is 512 megabytes, the idea being basically that you can burn them to a CD, so you can just take your collection of 100 arenas, put it on 100 disks, and now you have a physical backup you can put somewhere. Or you can just get a flash drive, but that's just me. But so what it basically is doing is it's just going, well, okay, every block we're caching is in one of these arenas somewhere. So if we just take that arena index, and well, each arena is 512 megabytes. If each block in that arena is 8 kilobytes, that's 65,536 possible blocks per arena, which is exactly 16 bits of indexing needed. So if you stuff that into just 2 bytes of which arena is this, and then 2 bytes of which block in the arena, and the second trick is that the cache, this is a cache. This hash table only exists for caching. The value will always be a buffer. It does not need to be able to cache an arbitrary pointer into memory, because it's not caching arbitrary memory. All it's caching is if it's set to, I mean, currently this needs to be parameterized properly. This was just the prototype from a couple weeks ago. But basically, if I'm caching a couple 100,000 entries, all I really needed to do is set aside memory for, okay, 8 kilobytes of data each. And then the value isn't a pointer to random memory. It's just which buffer in that list of buffers is it. And suddenly, it ends up being able to fit 8 of them per cache line right now with the lock in there. And there's a couple of changes I have to get that up to 12, but I'm not going to get into that now. I'm just going to actually get into the only other thing that as far as I know, is actually somewhat novel in how this cache works. And that is that this does not actually support gets and puts. It doesn't support either operation. Instead, it's more of an, absurd is the wrong word, but it probably evokes the accurate implementation a little bit more. What it basically is doing is going, okay, the only time you're ever going to access this cache is when someone is either writing or reading data. When that happens, we have the key. And either we already have the data because this is a write, or we need to know whether or not we need to read the data because it's either in cache or not, we're reading data. And so what it basically does is it just says, don't give me a value, ever. Just give me the key, I'll give you a buffer. It associates the key with that buffer, and so on read, what ends up happening, and the code for that actually will illustrate this a lot more than me talking about it will. But cache lookup. This is the entire code for reading a block from disk. And other than just the assertions to make sure things are correct, all it does is it says, okay, cache, here's the arena I'm working with, here's the block in that arena I want, give me a buffer for it, and tell me whether or not I've already read data into that buffer. And if not, it reads into it. All it's really doing is associating the key with that buffer and giving you the buffer back. And so the rest of it's just bog storage hash table stuff, linear probing, open addressing. It's nothing interesting or really worth getting into. But basically it just has this giant array of data and says, okay, anytime you want to insert data, we find the right bucket, which Fibonacci hashing, which basically is just multiply by the golden ratio to scatter around which bucket you're picking. And check if it's in the bucket. If so, grab the pointer, or grab the index, turn it into the pointer, and give it back. And so all this ends up being is, hey, is it in cache? If so, cool, return it. If not, let me read it into that buffer and done. And this ends up, again, this doesn't even show up on the profile anymore, just because it's nothing here takes all that much work. The entirety of the code for Neoventi fits in less space than the headers for Venti do, which I think sums up how much less, I'm not going to say how much less thought was put into it, but more how much more thought was put into not overdoing things. But again, it ends up being, looking at the profile, I think I have one lying around here. The entirety of that time, if I can remember how to actually output this. Multiple of them, cool. That's the wrong one, but Oh, and that's 5 seconds with the profiler enabled, to be clear. This is actually slowed down. That's why I said 4 seconds. It ended up being 5 because it was actually grabbing a profile. But a lot of this is just do things simple, do things right, and don't overthink it. And currently, it already beats Venti in performance on the read side for almost every case, and I'm going to have that to every very soon. Then it's just adding in the right code and moving on to NeoFossil instead. Because honestly, most of the problems with the Venti fossil system probably come from Fossil at this point still. But there's a lot of cool things that Venti enables that are very, very hard to actually do with Venti as it is today. I hinted at the fact that you can do load balancing with Venti because all of it's just hash-based data. You can put the data in multiple separate Ventis and just pick one dynamically. One of the things I originally was doing actually, I have a Venti on here, I have a Venti on a server at home. I can, when I'm online, only work on that one. The file system syncs to it. When I'm offline, basically just work on the local one and sync to it when available. So you can basically, and during the last 9 Front Hackathon in Brooklyn, I was able to synchronize my file system over the internet about 50 miles away in about 10 seconds. Because Venti because the data storage is append only, and all of the data just gets written to the end of the arenas, you can synchronize a Venti just by, for the first time, you just copy up all the data that's in there, and you write down where the data ended. So if it had 100 gigabytes of data, you would literally just need to write down the number 100 gigabytes. The second time you want to sync it, all you do is go, how much data is in here? Cool. From the 100 gigabyte mark to the 105 gigabyte mark, just copy that data and store it in the other Venti. And it can do this without having to look and without having to walk the file system at all. So if you have no data in there, it can detect that in under a millisecond. Literally the entire time is this network round trip. And there's a lot of these really cool features that should be really easy to do with Venti or really easy to enable. For instance, it stores data as a hash, Git stores data as a hash. Someone suggested earlier you can put Git on top of Venti, and I've looked into doing this. And the problem every time comes down to Venti just isn't maintainable. It's very hard to actually make changes to it, to actually add any kind of features you would want to it. One very obvious feature that it's missing, it stores all this data as hashes. If you have data on your root file system, assuming that this actually works with the compression, which I'm not convinced it does because the last time I tried this I had to patch it. But in principle, the file system is responsible for managing that score. So it should be able, no, that's completely wrong, that's corrupt. The 0 is at the end, that is not a valid SHA-1 hash. This disk has full disk encryption enabled, and trying to read back 32 bytes in the middle of a sector apparently doesn't go very well. But in principle, if you have the hash, you can just find the data. But the problem is if you're storing a lot of data in a Venti, you do not want to have to remember these hashes, you don't want to have to write them down somewhere. So it seems really obvious to just have Venti have a place to store this. A small key value store, something along those lines. But any change you make to Venti is going to have to deal with the fact that because of the way it was designed, there's a lot of places where it will rely on undocumented assumptions. It will actually violate its own stated APIs in some places. And there's a lot of these places where you go to fix it and you'll actually make it worse. And so one of the goals with Neoventi isn't just, hey, let me do the same thing but better. It's let me build this solid ground to stand upon, to actually start adding all of these cool features that should just work. There's these things that should be really easy to do that just aren't. And having a solid base to work with should hopefully make that a lot easier. And I will open the floor to questions now that I have talked you off for a while and crashed my file system only once, intentionally. That's a new record.
Do you actually run Fossil with Neoventi? Or Fossil?
I have run VacFS with Neoventi, which is what that walk was doing. In principle, you could run Fossil with Neoventi as long as you don't actually try writing data to it, since Neoventi currently does not actually have the write code in place yet, mostly because I wanted to get the caching in place first so that I could actually, basically, if I'm trying to actually test the write path and I want to write 5 gigabytes to it and it doesn't have a cache for the index data, that ends up taking a long time just because every single write has to flush to disk.
So you're using the arenas made by old Venti?
Yeah, that Neoventi example I was using there, that's actually running off of the file system that's running Neoventi. Yeah?
So just consider the Fossil only writes when it does it snapshots.
Yes.
So
In principle.
You can run your file system from. You just wouldn't be able to take any snapshots after that. But you could mess about with it more.
You could use it for the historical data. The basic problem is that at 5 in the morning it's probably going to crash. By default, you can change when it'll crash.
Well, you can switch on. You can stop it.
You can turn off the snapshots. But that seems like the easy way out.
One of the things that part of the history is that it wasn't perhaps the original intention that the moment a fossil had to be attached to a Venti, you could never have it go offline again.
Yeah.
It was a sort of side effect of the way it was done.
Yeah. So Jim used to tell this story about the first time he and Frasato tried to disconnect the fossil from a Venti, and then they just looked at each other and went, "Oh shit, that's not how it was supposed to work."
Yeah. Well, so, there were lots of reasons that I've always wondered about that structure that you mentioned about it has its own version of various things that are already there in Plan 9. Now, I wasn't sure, and I never bothered to ask anyone whether it was part of some plan to have it as trying to make some sort of product out of it, because they were looking for justification for themselves, and so they wanted to separate it from the Plan 9 source code base.
I have heard that suggested before.
I don't know whether it's true, but
I've heard that a couple of times actually.
Yeah.
And it would explain some of the decisions that don't really make sense otherwise.
I mean, it's interesting that there was a project, I completely forgotten about it actually, but I think it was a GSOC thing to do a Venti implementation from Burner.
I think someone did that, yeah.
Yes, and I've just looked at it now, and it's, I mean, it allocates more than you want, but I mean, that on its own is 757 lines of limbo, which is a lot smaller than the Venti, and it
Yeah.
wants to be able to do writes. I don't know whether it tries to cache it, look more closely at it. It's just
24,000 lines, and that's not even all of it. There's more that's missing from that.
I think everybody is aware of this problem, but that's one question. Actually, kind of two questions though. So would your Neo fossil be able to operate by a connect, disconnect, connect kind of model?
I've thought about that. One of the things I was working on, one of the things I was doing initially, which is why I started looking at the Venti source to begin with and throwing memory at it on here, was I wanted to have a Venti on the laptop and a Venti on the server.
Yeah.
The Venti on the server would be the primary one, and there would be a fossil on both that would stay in sync. Yeah. And the basic idea was any data that's important, like by default, you would want to keep some of the data on the local Venti too. But you would basically, I wanted to be able to differentiate between different file systems. So for instance, you'd have your root file system. You need the entire thing on every machine, basically, if you want to be able to disconnect. Because if you don't have the software on it, you're out of luck.
Yeah.
The other option for that, though, which I've been looking at, and actually, I mentioned, I ran into deadlocks, okay, like with Go, it's very trivial to deadlock fossil. Mm-hmm. A few months ago, I ran into one. I have the notes here somewhere, I'm sure. But the cause of the crash of the deadlock there was a case. It was very simple. There was a case, an error path where it wasn't unlocking. That was it. It was really, really simple once you knew what to look for. But the problem was the code was all intermingled, and it was a while to figure out which locks were even being held at the time. But one of the thoughts that the way I was able to even debug that in the first place, I don't know if you're familiar with the ants work that Mycroft did off of 9front and off of Labs 9 a while back. But one of the basic concepts there is that your terminals are rootless. They do not have a root file system. They boot into a RAM disk. That RAM disk is basically stored in 9FAT alongside the kernel. It's basically like an initial RAM disk on Linux, except instead of just being used to contain the tools to load your root file system, it is your root. And so it'll have all these nice things in it like Rio and ACID. So you can run Rio from memory, and in a window, you run your root file system. If the file system crashes, that window is gone, but you have your main window manager still, and you can open up ACID in it and attach to that dead root file system. And so that's what I was able to do, is I was able to actually get a backtrace of every thread that was hanging at the time when fossil deadlocked. And I honestly don't think I would have been able to debug it without that. But one of the thoughts I've had regarding the NeoFossil solution is, instead of trying to actually synchronize the root file system between all the machines, stop trying to use a root file system, so that when you're offline, if some data is missing, some programs are missing, that's fine, because anything that you actually need to be local is going to be in RAM.
That makes a ton of sense.
And it simplifies a lot of the problem, because you don't have to worry about, how do I make sure that I have enough space on the local Venti. It means that, like, you can toss this on a 16 gigabyte micro SD card for a Raspberry Pi and not have to worry about running out of space for it.
So that's really nice. Right toward the end, we were doing that on Harvey too, and it was great. Just screw this root file system thing, it's long memory. But the next question on the Camly store, which has a new name now, which is a hash file system done back in the day, they decided from the beginning to prefix the SHA with the SHA type. The idea
so that you can change the hash.
So I don't have to tell my grandchildren that I used the wrong hash.
Yeah, that's one of the things Neoventi, basically, the work I have is effectively split into two phases. Phase 1 is replace Venti. Phase 2 is fix up the actual underlying system. Yeah. Because, and this is what I was getting at earlier, there's a lot of, Venti gets a lot of things right, but there are some things, it uses SHA-1 for the hash. I'm looking at, for I haven't done enough research into this to have a definitive answer, but I'm currently leaning towards Blake 3 as a replacement, since it's supposed to be a lot more, it's supposed to be more secure at this point, like for hash collision resistance, and also it's a lot faster than any of the competitors as far as I know, and it's simple in C, so it can just be included. But in general, one of the things I've been looking at, and this is after the thing is done, is not just replace the hash once, but keep track of what the type of the hash is, so that it can actually be swapped out. The problem with that is you end up in a case where, if I have right now on here, what is it, 13032? If I have on here 100 gigabytes of active storage right now, and I switch the hash to something else, I have to be able to use the old hash to read the data back.
Yeah.
So not only do you end up in the problem where you basically have to change the protocol so that you can specify the hash with the which the hash is.
It's a change.
Just have a byte in the score to specify the hash.
I think I would need to double check, but I'm pretty sure the protocol actually hard codes the size of the score right now. So I'm pretty sure that would still be a breaking change to the protocol.
Yeah. But
because of how it's designed.
You'd be the first person to use a new version number.
I already did bump the version there, because there are some things where I am technically breaking compatibility, just because there's things that Venti technically supports that it doesn't actually care about, and I just went, I'm not going to bother even pretending to support them right now. Yeah. Like the first string, if I shouldn't do this, but in principle it's probably fine. I think I'd have to actually post to it for this to do anything, though. In principle, if you make, what is it, dial? Aux dial. In principle, if you dial a Venti server, it gives you a version string. Yeah. That whole string, nothing actually cares about it. The only thing that any of the implementations do, Neoventi, Venti, and as far as I know, the Go one also, I didn't spend enough time looking at that to say for sure though. All it does is say, okay, now I'm going to read one byte until I find a new line and assume that all of this is garbage. All it does is make it harder to parse the hello and to figure out where to actually start the connection. If they literally just put this version string in the hello message, it would be easier to parse. But I didn't design this. I'm just dealing with the aftermath. But yeah.
I'm curious. You said that your Venti is slower doing the cold read than the old Venti.
Yes.
Have you looked into why?
I have not profiled it to figure out why, but there are some very compelling reasons just off the top of my head, which is old Venti will read the entire arena after you read like 3 blocks from it. So it's going to have most of the data in memory before the client requests come in, which again, given the profile shows most of our time is already spent waiting on the client. That's after the cache is warmed up. It's most of the, The other thing there is Venti has that index cache, basically what that means is that when it loads in a bucket, it's gonna load multiple entries and unpack them all at once, so that the next lookup. Some of the things it's doing make it slightly faster to find the data that you're looking up to begin with, is what a lot of it comes down to. I also don't remember if I ended up hacking the index into the cache at all yet, so this might technically not have an index cache, which, given that this workload in particular, that archival file system, because it's a fossil score, that means that it has the dump from like 50 consecutive days, and most of the files are the same. Which means that because it has the index cache and it's already got those unloaded during that cold run, it ends up able to skip. I say it ends up able to skip the index, but the truth is that the activity light goes on when it's doing the warm read, so I'm not going to pretend to understand what Venti thinks it's doing anymore. I gave up on pretending that a while ago. There's a lot of things that the documentation will say one thing, and it's pretty obvious that that's what it's supposed to be doing, and then it ends up doing something that's very different. So just because of emergent behavior, where it'll end up thinking it put something in cache and then we're dumping it out 10 seconds later, even though it has plenty of available cache room. So there's a lot of assertions in the man page about how you need to set the cache to XYZ size in order to make sure that you can sustain a certain throughput, and all of those numbers are completely and utterly lies. None of them has any connection to reality, because what the code is doing is not what they claim it's doing.
Is some of it just the factor that in 2002, 2 gigabytes was big?
Some of it is. Some of it is definitely also that a lot of this didn't matter when your workload sizes were single-digit gigabytes, double-digit gigabytes. Because if 10% of your workload fits in your 1 gigabyte of cache memory, then it's very different. Yeah. But at the same time, this particular case makes me think it's not just that, simply because this is not a huge archive. This file system that I was running through is, this is including all the fact that there's multiple copies of everything in it, and it's still 2 gigabytes, because this is the home folder. It's largely like text files and code. With the archives, it's 2.2 gigabytes. So and just walking the tree with Venti with a warmed up cache takes 12 seconds, if you're lucky. Some of it comes down to the design not being optimal for today's systems, but some of it, the signed 32-bit integers for memory sizing thing is easy to laugh at now and go, why would you ever think signed integers? But at the same time, if your memory is less than 1 gigabyte, it doesn't really matter. Because it's wrong, but it's just an int. It's not like you specified signed, you just didn't think about it.
Well, also apparently there's a bug in indexing things with unsigned values.
That's true, but given that I fixed the bug in Venti before that was fixed.
No, I was looking back at really old source, and there's this comment about there, save more for the big boys. Well, the big boy was the 36 socket SGI machine that had 128 meg of memory, which was this
some of it.
This is a large amount of memory. So
on the other hand,
well, not really anymore, but yeah.
On the other hand, you also have things like it has a disk scheduling routine, where basically every time it goes to make a disk access, so if it's for the index, for the arena, whether it's read or write, it keeps track of it. Yeah. So it looks at the last time, and then if you, anytime you want to make a request, you call this function, and it basically says, we're going to check how active the disk is for reads, how active it is for writes, and based on whether or not the workload you're trying to do is prefetching versus actually grabbing data that the client is asking for, it'll make you go to sleep and wait. Wow. And I had an experiment. I stripped this code out and tested it in various workloads, and I literally couldn't tell the difference. Yeah. And this is one of the things where I think it might actually just be that, hey, it made a lot more sense on older machines where it was more affected.
I had an interesting conversation with the storage person at Google about actually 15 years ago now, and I said, with the disks you guys get today, how many games does it make sense to play in terms of optimizing performance? And he said, basically none. They're already so optimized internally, you're unlikely to do better.
To comment on it. First, even spinning Rust has native command queuing, so it'll reorder your IOs.
Yep.
But the other question, Have you actually tried this on Spinning Rust, or has it all been SSDs?
I did try it on Spinning Rust a while back. Unfortunately, well, actually, I was about to say 1,000 miles. My server is currently a couple hundred miles away and has been decommissioned for a while for noise reasons. So I haven't tested it on that.
Say noise reasons?
Noise reasons. I kept it in the bedroom and it was loud. And I decided that my sleep was more important than having a 24/7 Spinning Rust thing on. Yeah, but but yeah, some of this is stuff that I'm not certain I can believe. I would need to test this to decide whether or not it made sense when it was implemented. But a lot of it is stuff where a lot of it is stuff where it really does look like this was a prototype. And I mean, that was explicit in the paper, for instance. This was an experiment, and the fact that they ended up actually using, I mean, okay, one of the things that makes me lean towards the hypothesis that they were looking to commercialize it at one point is the fact that it has code for generating stat graphs for statistics that under no circumstances do you actually need to know, because they tell you nothing useful about what Venti is actually doing. But it's the kind of thing I could imagine that they would think would be like, hey, we have pretty pictures of what's going on.
Also, they have JavaScript.
In Venti?
I'm pretty sure it serves some HTML with JavaScript.
It serves HTML, but I have not seen any JavaScript in there.
Okay, I could be wrong about that.
I'm scared now, but I don't think so. It has these endpoints for doing things, but
Yeah.
I don't think it does.
But nobody on Cloud 9 is using that. Right.
It generates, I mean, the HTTP server is basically really only useful for getting the information you need to do to copy from one Venti to another. And that's really the only reason that this server should even exist right now is because the protocol is missing some requests.
Yeah. Oh, no, I'm wrong. I don't see the JavaScript.
An alternative I've often thought of doing, but I haven't had the time to, was to rip that out and put an IP server in so you get information from IP.
That is in the paper as one of the things that I want to do.
I didn't read these things to avoid spoilers.
No, that paper, honestly, I need to rewrite it. It was very rushed. But the talk was better than the paper, and that says something.
Too important and using scripts and so on.
Yeah, I've definitely thought.
Whereas if it's in the protocol, you'd have to have new protocol messages, well, the usual problem, new protocol messages from new metadata, and I think protocol being focused on just the basic caching.
I kind of want to just kill the protocol entirely and just use 9p, because if you can just mount the Venti and go, hey, oh, right, the aux styles.
That would be very nice.
You could, in principle, just be able to do, hey, cat some hash here.
Yeah.
Or you could you could build on top of that and do something like what GitFS does and just go, hey, we have this hash tree. Let's just, you access the tree, you access it as the file system directly. There's no particular reason it couldn't just synthesize this on demand. Toss fossil in there, like fossil. Just toss in some hierarchical system in there while you're at it, and a lot of this could be a lot simpler. If you had, basically, if you toss in just some light key values read-write buffer into Venti itself, you could use that for storing root scores so you don't have to memorize them, so you don't have to store them in your file system, which is itself stored in Venti.
I think I'd probably do that as a separate service so that it's composed and focused.
Yeah, there's...
I agree, you don't want to store them locally.
Yeah.
For most us, there's never lost the score.
Exactly. I know Mycroft for Ants had a system where it would automatically back up root scores into 9FAT. So that if the system crashed, it could automatically grab the list from 9FAT, grab the latest one, and reinitialize your file system for you. I don't remember if the script actually did that, but it definitely had the information too, because I remember looking at that and going, huh, that's neat. I should play with that more, and then never doing so.
Maybe it's for Mac, but from the server you can list them chronologically. Then you can take the last one and hope it was the whole one.
You're saying if you were to store these in the server?
You can get them back to the server. But
You can scan Venti for all root scores. The problem is because basically the way that it does this is it goes, okay, root score. We know what a root. We don't have a list of root scores. What we have is we have the data log and we have the index. The index is useless. We're going to ignore it. We look at the data log and we just go, okay, I have 94 gigabytes of data. That's rough. If we look at it here, that's roughly 14 million blocks. So what it does is it goes, okay, let's read every single one of those 14 million blocks and check if its type is root. And if it is, print its hash.
Yeah, I've done that. It takes a while.
Yeah, it's not only just that it takes a while. A lot of the Venti tooling, again, this comes down to a lot of this. The ideas are good, but the tooling, setting up a Venti server is too complicated.
I believe that everyone was rushing off to Google at the time.
Yeah.
A lot of it. I mean, okay, one example of this.
Everybody involved was rushing off to Google. I mean, you know.
One example of this is the tool that you use to write data, raw data to Venti, the write arena. Basically, you grab the arena from one Venti, pipe it over the network, and then you pass it to this tool, and it will just take that arena and put the whole thing in. So if you do this to every arena on the source Venti, copy and just insert the entire thing in the destination, it will synchronize the entire Venti start to finish. And you keep track of where you left off. The next time you do it, you start at the end of the arena, and it can just not have to look at any of the old data. What I described is how it works in 9front as of the hackathon when I fixed it. Before that, it would actually do, even when it had, basically it would scan the data it already knew that it didn't need to. And the way it did it was, suffice to say that I effectively inlined a solid third of Venti's arena reading code and then cut it in half, because a lot of what it was doing was completely and utterly unnecessary even in the normal case, and I just didn't bother fixing it there. But a lot of it really is just, basically what it's able to do is just, now, if I run this, I mean, I don't have a remote machine online right now to actually do it with, but now it can, you can actually do it on the arenas you've already copied, and it'll detect it automatically quickly. And it can, a lot of this was really just, the main thing is it just reads the entire arena into memory at the start and then just sends it over the network. Whereas before it was actually going through the Venti logic and caching. And it was spending more time evicting its own entries from cache than it was actually sending data over the network. So again, there's a lot of this which is just, one of the things I also want to do with Neoventi is actually write a replacement for libventi also, so that a lot of this tooling can be cleaned up and improved and expanded on, because it would be really cool if we could actually just put Git on Venti, or if we could actually just have a load balancer or a cacher or torrenting, for instance.
Load balancing with the hashes, you do something like chord, for example, to circular hash to serve around a set of servers redundantly.
Yeah, there's a lot of these things that the tooling either doesn't exist or is so haphazard that it's harder to figure out how to use it than to rewrite it from scratch. This tool is technically documented, but the best documentation of it is the RC script that was lying around somewhere on, like, without, yeah. A lot of it is just really good ideas that could be done a lot better, and basically, it's very easy for me to come in 20 years after this was done and go, I can see all of the things you did wrong and I'm going to fix them. But I can only do that because they did this 20 years ago, because people have worked on it since then, and it's very obvious in hindsight what the flaws are. The only reason that my solution wins right now is because I had this to use as a reference of what not to do. Basically, they took, normally, for my own projects, for instance, there's a compiler project I've been working on off and on for years. I have thrown out the entire code base 6 times now and started over. And with Venti, I got to cheat because they already did it for me. So it's not so much, I don't want the message here to be, oh, Venti is terrible, Venti sucks, Venti is really poorly implemented. Venti is a really well done system that was just done with no prior art to work off of. I'm not coming in and magically fixing things. I'm just coming in and going, okay, now that you gave me this framework that I can build on, I can see what you did right, I can see what you did wrong, and I can make it more cohesive.
Well, there's similar things with Fossil, where it potentially spends a lot of its complexity fussing over buffering stuff. And as you get into SSDs, let alone NVMEs, I don't know. Buffering, because it's trying to organize dependencies amongst the things, so that it puts things out in a safe order.
That's definitely true, but there's also a lot of what it does. When I did test it on Spinning Rust, it wasn't faster there either. For all I know, that's just because modern spinning Rust has the SSD cache built in, like the DRAM. I think like 32 megs might not sound like a lot, but when you're talking about 8 kilobyte blocks, it might mean the difference between needing a couple hundred lines of. Basically, we don't have like. Yes, like Ori pointed out, the spinning Rust disks do have queue management on the chip in the disk itself.
Well, but that can also work against clever logic that tries to arrange dependency.
Exactly, but
well, we'll just shuffle things ourselves.
but it is worth noting that even if those same systems existed when this was first designed, which I don't think they did, they definitely weren't the same or nearly as complex as they are now, where now it's basically just, an ARM chip that they toss in there, give it on some of the terabyte, like if you have a 4 terabyte spinning Rust disk, I think they give it something like half a gigabyte of DRAM. So it has a lot of resources. Like the microcontroller in a spinning Rust drive now is almost on par with the computers that they were working with originally. So yes, a lot of this complexity is silly and can be thrown away even on systems that feel old now. But that doesn't mean that it made no sense when it was written. It just means that history has changed. We've moved on and it doesn't make sense anymore. On the other hand, a lot of this never made sense. The layers of abstraction, to the best of my knowledge, have not been optimal on any computer that has ever existed. And I'm fairly sure there are multiple programmer Bibles that will effectively say this is exactly what not to do for optimal code. Just because, I mean, it's less of a problem for us, or possibly more of one actually. We have less fancy optimizations in the compiler that this kind of abstraction can interfere with. But on the other hand, we also have things like completely no inlining. So suddenly tossing 20 unnecessary function calls in a hot path can actually be a problem if you're shuffling a lot of memory around when you don't need to be. But I mean, it says something that Venti is actually accessing the disk when the cache is warm, even though it's full. That's pretty symbolic of the kinds of issues that I was dealing with trying to fix the system. Or the packet code is a great example. Venti has a packet layer. The libventi, which is the core of the original Venti server, basically. Original might not be fully accurate. So this is about 1,000 lines of code for managing fragmented buffers. The main problem I have with this is that those fragmented buffers don't actually exist. And to the best of my knowledge, every single one of these has a frag of 1, except for when it is synthetically splitting buffers in 2 to insert stuff in the middle, in which case just stop doing that. But
well, again, I wonder whether that was part of some. Well, it will eventually deal with IP level fragments directly itself.
Or this code satisfies our claim in the patent.
So the Western Digital
True. Yes.
Western Digital 16 terabyte doesn't have gigabyte cache.
So if there are any other questions, I think we'll probably take it to the bar or
Yeah.
down here. We'll figure it out.
yeah.
That's terrific.